Hi, today I will discuss the Newton's third law of motion and equilibrium of particles. But first, let me introduce myself. I am Karen Navalopez, your teacher for today. Before I proceed to the main topic, I will introduce to you first who was Isaac Newton. Isaac Newton was an English scientist and mathematician famous for his discovery of the law of gravity and also the three laws of motion. Today, these laws are known as Newton's laws of motion and describe the motion of all objects on the scale we experience in our everyday lives. Newton's third law of motion. For every action, there is an equal and opposite reaction. In this figure, F sub 12 may be called the action force and F sub 21 the reaction force. Actually, either force can be the action or the reaction force. The action and reaction forces act on different objects. Newton's first two laws of motion explain how the motion of a single object changes. However, Newton's third law describes something else that happens when one object exerts a force on another object. If body A exerts a force on body B, then body B exerts a force on body A. According to Newton's third law of motion, forces always act in equal but opposite pairs. These two forces have the same magnitude but are opposite in direction. These two forces act on different bodies. This means that when you push on a wall, the wall pushes back on you with a force equal in strength to the force you exerted. The forces exerted by two objects on each other are often called an action-reaction force pair. Action and reaction force pairs don't cancel because they act on different objects. Right now, gravity is pulling you down in your seat, but Newton's third law of motion says your seat is pushing up against you with equal force. This is why you are not moving. There is a balanced force acting on you. Gravity pulling down, your seat pushing up. Think about it. What happens if you are standing on a skateboard on a slippery floor and push against a wall? You slide in the opposite direction because you push on the wall, but the wall pushes back on you with equal and opposite force. Why does it hurt so much when you stub your toe? When your toe exerts a force on a rock, the rock exerts an equal force back on your toe. The harder you hit your toe against it, the more force the rock exerts back on your toe, and the more your toe hurts. Another example. Consider the interaction between a baseball bat and a baseball. The baseball forces the bat to the right, and the bat forces the ball to the left. A variety of action-reaction force pairs are evident in our nature. Consider the flying motion of birds. A bird flies by use of its wings. The wings of a bird push air downwards. Since forces result from mutual interactions, the air must also be pushing the bird upwards. The size of the force on the air equals the size of the force on the bird. The direction of the force on the air is opposite the direction of the force on the bird. For every action, there is an equal and opposite reaction. Action-reaction force pairs make it possible for birds to fly. Another is the propulsion of a fish through the water. There are action-reaction force pairs. Action-reaction force pairs make it possible for fish to swim. Another is the motion of a car on the way to school. There are action-reaction force pairs. Action-reaction force pairs make it possible for cars to move along a roadway surface. You constantly use action-reaction force pairs as you move about. When you jump, you push down on the ground. The ground then pushes up on you. It is the upward force that pushes you into the air. Another, in this figure, Newton's third law of motion explains how the boy starts his skateboard moving. There are action-reaction force pairs. The forces causes the boy to move forward. Remember, Newton's third law of motion states that every action has an equal and opposite reaction. This means that forces cannot exist alone. Forces always act in pairs. Action-reaction pairs don't cancel because they act on different objects, not on the same object. Equal and opposite forces acting on the same object would cancel. So far, I have discussed Newton's third law of motion and analyzed some examples. We can now proceed to the main given problem. A car is skidding to a stop on a level stretch of road. Identify all the action-reaction pairs of forces between the car and the road surface. Then, draw a free body diagram for the car. The most important step in solving problems involving Newton's law is to draw the free body diagram. The free body diagram can simplify the problem. Shown is the free body diagram for the problem. There is normal force N, friction force F, and the weight. For the given weight of the car, normal force, and friction force, we are required to find the action-reaction pairs of forces between the car and the road surface. In the given problem, there is no mathematical formula applied, yet concept of Newton's third law of motion is applied. In the given situation, action-reaction pairs are, first, the normal force exerted on the car by the road and the normal force exerted on the road by the car. Second, the friction force exerted on the car's tires by the road and the friction force exerted on the road by the car's tires. Third, the gravitational forces the car and the earth exert on each other, which is not a force exerted by the roadway, so it doesn't count for the problem. However, there are two pairs of action-reaction forces between the car and the road surface. To conclude, there are two pairs of action-reaction forces between the car and the road surface. First, the normal force exerted on the car by the road and the normal force exerted on the road by the car. And second, the friction force exerted on the car's tires by the road and the friction force exerted on the road by the car's tires. Let's proceed to the next topic, equilibrium of particles. A body is said to be in equilibrium when it is at rest or moving with constant velocity. We must remember that the net force acting on the object is zero. There are two types of equilibrium, which are static equilibrium and dynamic equilibrium. Static equilibrium. If some forces are acting on a body horizontally or vertically, and the body remains in states of rest. Example, a book lying on a table. Dynamic equilibrium. If some forces are acting on a body horizontally or vertically, and the body remains in states of motion. Example, a train moving with uniform velocity. Let's now proceed to the given problem. Bethany, who weighs 560 Newton, lies in a hammock suspended by ropes tied to two trees. One rope makes an angle of 45 degrees with the ground. The other makes an angle of 30 degrees. Find the tension in each of the ropes. Shown is the free body diagram of the problem. For the given, we have weight of Bethany, rope 1 angle with the ground, and rope 2 angle with the ground. We are asked to find the tension of rope 1 and the tension of rope 2. To solve the problem, we are going to use this formula. For the solution, in the horizontal direction, T sub 1 cosine 45 degrees equals T sub 2 cosine 30 degrees. Cosine 45 degrees is equal to 0.71 and cosine 30 degrees is equal to 0.87. It will result to T sub 1 times 0.71 equals T sub 2 times 0.87. Then, T sub 2 equals T sub 1 times 0.71 divided by 0.87. The result is T sub 2 equals 0.82 T sub 1. In the vertical direction, T sub 1 sine 45 degrees plus T sub 2 sine 30 degrees equals weight. Since sine 45 degrees is equal to 0.71 and sine 30 degrees is equal to 0.56, it will result to T sub 1 times 0.71 plus T sub 2 times 0.56 equals weight, which is 560 Newton. And then 0.71 T sub 1 plus 0.50 T sub 2 equals 560 Newton. Now, from the equations 1 and 2, 0.71 T sub 1 plus 0.50 multiplied by 0.82 T sub 1 is equal to 560 Newton. Since 0.50 times 0.82 T sub 1 is equal to 0.41 T sub 1, it will result to 0.71 T sub 1 plus 0.41 T sub 1 equals 560 Newton. Adding 0.71 T sub 1 and 0.41 T sub 1, it will result to 1.12 T sub 1, and the equation will be 1.12 T sub 1 equals 560 Newton. Then, T sub 1 equals 560 Newton divided by 1.12. The result is 500 Newton. Hence, the tension of rope 1 is equal to 500 Newton. From the equation, T sub 2 equals 0.82 T sub 1, using the value of T sub 1, we can get T sub 2 equals 0.82 T sub 1. Substitute 500 Newton to T sub 1 and the equation will be T sub 2 equals 0.82 times 500 Newton. The result is 410 Newton. So, the tension of rope 2 is 410 Newton. To conclude, the tension of each ropes are 500 Newton for the rope 1 and 410 Newton for the rope 2. Again, I am Teacher Karen. See you in my next video tutorial. Thank you and God bless. Bye!